Okay, so in this lecture we're going to talk about convolution, and we're going to end with convolutional neural nets. But first we have to talk a little bit about the history of convolution in computer vision. So of course this is something that's intended to be applied to image data, and we'll shortly see why image data is particularly it's conducive to using convolution. So first of all, how should you think about the structure of image data? So it's a large tensor, typically, is what an image is. So if we have an image x, then the way we should think about that is that, for example, if we have an RGB image, each of those RG and B correspond to different channels, right? And those channels correspond to different wavelength frequencies. Sorry, doing a poor job here. And they can be thought of as matrices, each channel, so R, G, or B, where you have x11 for the first channel, and x12 for the first channel, and so on, x21 for the first channel, and so on. And then the next channel, so in RGB, there's 3 different channels, x11 for the second channel, x12 for the second channel, x21 for the second channel, and so on. Right? And so for RGB you would have 3 channels. For multispectral imaging you would have more channels. So for example, for X-ray data you would have a channel corresponding to the X-ray wavelength range. And so that's in general what an image is going to look like, is some tensor, which is number of channels by the pixels in the X and the pixels by the pixels in Y. Right? By the pixels in Y. Right? And so a lot of times in like TensorFlow, for example, you're going to see that they're expecting your tensors to look like channels by pixels. And this is partly why we end up constructing some like 4-dimensional or order 4 tensors in TensorFlow, because we might have something like the mini batches times the number of channels times the number of pixels by the number of pixels in the Y. Okay, so in earlier, before convolutional neural nets really became the standard tool for doing image analysis, people would define filter banks, which are predefined, predefined operations for images. So let's just define them explicitly. So a filter bank, this is, you can sort of think of them as our small predefined images, small predefined images. We'll just say, we'll just call them predefined images. So they're, in general, they're tensors, such that each element phi, which is in this filter bank, so capital Phi is the filter bank, it's when we apply it to an image, we get a single number. We get this inner product between phi and our image x, which is just equal to the sum over j and k over all indices of this phi j k xj k, and this is for a single channel image. In general, you can have multiple channels for both, and then you would just sum along the channels as well. Or you could apply the filter to each channel individually. But a filter bank is really just a set of tensors that, if you wanted to sort of see how much of that, how aligned the image is with the filter, then you would you would take the inner product between the filter and the image itself. So why would you use this? Well, for example, if you were trying to detect an edge in a certain location in a certain direction, then you could define a specific image that's supposed to pick out an edge in that direction. Right? So an example of this is the Gobber filter. So our next definition is the Gobber filter. And for the Gobber filter, there's several parameters. There's the wavelength, lambda parameter. There's an orientation parameter. Call it theta. There's a phase offset parameter. And this is a bit more detailed than we require, but it's good to go through this just to see how difficult it is to come up with with filters that are targeted towards certain image types. There's a bandwidth parameter. This is sigma. And an aspect ratio parameter. So there's quite a few parameters, and they all have some sort of intrinsic meaning based on images and image processing. So what you would do is you would take a given position in an image and transform it to make it x tilde. So a position is a pixel position, so like ij pair. You would transform it by rotating it. The cosine of theta minus sine of theta. And then pardon me. And then sine of theta and then cosine of theta by x. Okay. And this is our position in the image. So think of the image as either ranging from, like, for example, 0 this position in the image could be continuous, a continuous location in 0, 1 by 0, 1, or it could be an ij pair, but we are going to rotate everything, and the effect of this rotation is just to change the orientation of the edge that we're trying to detect. Okay, and then let's define our filter as g of x, which you have all of our parameters, all of those 5 parameters. It's equal to the exponential of negative x tilde 1 squared plus gamma squared x tilde 2 squared over 2 sigma squared times the cosine of 2 pi over lambda x tilde 1 plus c. Okay. And what this function looks like, and we're sort of thinking of this in a continuous domain, but we can just put in like a standardized pixel location as our x. The way that this looks is that there are these level sets, which if the orientation is in a certain direction, there's a level set where this g is equal to 0 along a line, and then there would be other lines along which g is also equal to 0. So you can think about this as our image, for example. And then the other level sets of this filter are you have a positive region here, and the level set might look like this. This is a positive region, and then you would have a negative region here, and the level sets are also ellipsoids here. So if you're looking sort of along this normal direction to this plane, then it should look like a sinusoid that has diminishing magnitude. So this should have diminishing magnitude here. Sort of hard to visualize this just in 2D, but the basic idea is that in some sense you're taking the height of the pixels, so the pixel intensities on this side over here, and subtracting it, adding that, and then subtracting off the pixel intensities over here, so that if you have an edge, like where the pixel intensity is larger on this positive side, then you're going to get a positive value for this filter when you take its inner product with the image itself. So, so this was sort of the state of the art a while back for image processing, is you would create these filters and then that would form features for yourself. That would give you features, right? And then maybe you would do other processing things. So these features themselves are sort of designed to detect edges. Okay. Now we could change a lot of things about this. We could change its location. We could change its orientation. We could change the sort of amplitude of these fluctuations. We could change the width of these fluctuations. Yeah. In 1D, we can look at what this is, because you could also work with 1D tensors, which would be like time series. It would end up looking like the following. It's a sinusoid with that's sort of skewed symmetric here, with decreasing amplitude. Okay. And then if you take your inner product, say if you take the inner product of this Gobber filter with an X, which has sort of a change point here, then when you take the inner product of this with this, you would end up getting something that's significantly larger than 0, and you would detect this edge at this location in this orientation. And then we can center this by applying a shift operation. We can recenter this by applying an appropriate shift operation. So given a filter, G, we can center these anywhere. Just by shifting it. And so the way that we would do that is we would just define a shift operation, which would be like S sub delta X of G, so a shifted version of G at some pixel location little x. This is just equal to G of X minus del of X. So if you had such a filter, such an edge detector, you could detect edges anywhere. So for example over here, just by shifting the filter itself. And so this is a way of getting entire filter banks just from a single filter, is just by applying this shift operation. So for example, suppose that we had a filter which was a smaller image, which looked like the following, and then we applied it to an image which was larger, which looked like the following. Right? So maybe this is a 20 by 20 image, and maybe this filter is 2 by 2. Then, now let's imagine applying this shift operation and taking the inner product of this smaller filter image. So when we take an inner product and there isn't equal sizes for the two filters, then we would just take the inner product in the points where they overlap. So for example, if we didn't apply any shift, then the first inner product that we would do would be placing it up here, right? Placing the filter up here, and then because and so up here there's the delta x is equal to 0, 0, 0, okay? And then because the blacks would give you an even So imagine that these values are 1, 1, and these values are 0, 0 for these pixel values, and the values here are just 1, 0, 0, 1 in these corners of this image. Then when you applied it here, you would get that the inner product between these would be the 1 plus 1, which is 2. But then say you centered it precisely here by applying a different shift operation. So this is del x is equal to, it would be like 9 by 9, so that you shift this so that it's over, right over the center. Then you would get, let's actually make this a little bit different. Oops. Instead of zeros, let's make it -1. There's nothing keeping the pixel values from being negative. Let's make it 1, 1 in the black and -1, -1 in the black there. Then this inner product would be 0 in this first location. In the second location, you would have this value here would give you 1 times 1. So it's 1 times 1. Plus the next pixels would be -1 times -1, right, in the white pixels, because they overlap with white. And then 2 times this. Right? And this is going to be equal to 4. Mm-hmm. And so I think that the way that we can think about this is that when you take a given filter here, so for example, this small checkerboard pattern, and apply it to the image, if you shift it enough, it's going to be detecting locations where you have a similar checkerboard pattern that matches the checkerboard pattern that we're trying to apply. So this is how we can think of convolution, because the definition of convolution is the following. So given images, G, and then X, this is the convolution, and it's defined in the following way of G and X. It's defined as another image where G star X, if we look at the H location of this is equal to the sum over Z of G of H minus Z and X sub Z. And so one way that you can get, and then here you should think of this G as being equal to G of H minus Z as being equal to phi of Z minus H. So I've sort of reversed the role of the indices, and this is the actual definition of convolution. If you take this phi of Z minus H, well, I shifted it by taking, here, if you look at this should be the same as this here, right? So if you take a filter, and instead of the location, you shift it by H, then you're taking the indices and subtracting off H from the indices. And so that's the shifted filter. And that's going to be our G of H minus Z. And that's what we're going to take the inner product of with respect to this X. And so the G is like a flipped version, both vertically and horizontally. It's a flipped version of the original phi filter. And so this is the strict definition of convolution. And remember, this is in multiple dimensions. H is like a 2 vector for images, grayscale images, and for higher order tensors you can define it similarly. And so you can think of the convolution as the inner product of X with the entire filter bank that's constructed by shifting your given filter into every possible position, because you can think of this H as each position after shifting of the phi filter. Now this phi filter, I drew it so that it was overlapped with the original image. But then suppose that it went off of the original image. when I apply h. And you can easily do this by setting h to be large enough, like 20 by, like even 1919 in this case. So what do we do in these cases? Well, this is determining what type of convolution we have. So a full convolution, this is just going to pad xz with zeros for the z's outside of the bounding box. So whenever I need a value of x, if I'm trying to shift the filter outside of the bounding box of the image, then I'm just going to give it a 0 in that case. Now, valid convolution is just going to disallow this type of shift operation. So valid convolution is so G star X sub H is only defined when S sub H sub G is contained in the bounding box of X. Bounding box. Okay? So these are the two notions of convolution that you should be aware of. And so there's some history of using convolution on fixed filters. So for example, with Gobber filters, and there's another sort of filters called sift filters, and other wavelets, and wavelets in general. This was sort of the state of the art with image processing. Basically, the way you would do it is you would take X and you would apply a filter bank, which would include convolution and maybe some sort of reduce operation. And then you would vectorize this, which just means that it would then be, you would turn those into features that would then be fed into your favorite classifier. That could even be a multi-layer perceptron. Right? Now it turns out, a note, via the convolution theorem, you can apply the fast Fourier transform. So the FFT can quickly compute convolution. Now this is particularly useful on CPUs, but on the GPU actually we apply convolution just by using tensor operations. Another thing to note is that this is the strict definition of convolution, and it sort of reverses the order of the indices. Remember, this was equal to sum over z of phi of z minus h x z. This is actually not convolution. This is called the cross correlation, or that's what they call it in TensorFlow. And so when you see convolution used in TensorFlow, a lot of times they actually mean cross correlation, and that's when you take your original filter and don't actually flip it. So just be aware that there's this convention change. It doesn't change anything about what convolution actually does. It's just that in convolution you should think of your filter as being flipped before it takes the inner product, before you shift and take the inner products. Whereas with cross correlation, it's the opposite. You don't shift it, or you don't flip it before you shift and take inner products. So this is what convolution is, and next we'll describe how convolution is used in neural nets.